Hello, Honors Chemistry, and welcome to Chapter 8, Sections 8.1 through 8.4, an Introduction to Stoichiometry, implying that 8.1 through 8.4 is like the easy version of what we'll talk about in the next lecture. Now, the beauty of this is that stoichiometry is just another type of dimensional analysis. When dimensional analysis, like we've talked about since Chapter 2, is just the art of doing conversions, right? Is taking the concept of a relationship, right? And just in the context of science, figuring out how to use it, right? We've been talking all year about the concept of ratios, which are relationships, right? The only new conversion factor in this section, right, is the concept of a mole ratio, right? Which is the relationship between moles of substance A and moles of substance B, defined by the coefficients of a balanced equation. So note that there are a couple of things in here, right? So one, this implies that you can write formulas, correct formulas for reactants and products. Two, that you can balance that equation and then use those coefficients to relate moles of A to moles of B, right? Where A is any one substance and B is any other substance. Note that when we say that this is a relationship, right, what we mean is that it's not how much you have, right? How much you have is defined by the context set forth in the problem, right? The relationship is the only thing that you can glean from the coefficients of the balanced equation. For example, right, recipes. We all hypothetically have some experience reading a recipe. Here is a recipe to make 2 grilled cheese sandwiches, right? So then if I have 4 slices of bread, right, plus 2 slices of cheese, right? That's going to give me 2 sandwiches, right? That's what that relationship is, right? 4 to 2 to 2, right? That doesn't mean that I have 4 slices of bread on the counter. It doesn't mean that I have 2 slices of cheese in the fridge, nor does it mean that I can have 2 sandwiches, right? These are all just relationships, right? And it's the same thing in a chemical equation. When we look at a chemical equation, for example, over here, we've got this relationship between the components of water, right? So this says that 2 hydrogen react with 1 oxygen to produce 2 water, right? These are the mole relationships for the production of water from hydrogen and oxygen, right? So I could say that 2 moles of hydrogen are equal to 1 mole of oxygen, right? I could say that 2 moles of hydrogen can produce 2 moles of water, right? Yes, does that make sense? I could also say that 1 mole of oxygen could produce 2 moles of water, right? These are all relationships that we can glean, right? I could even say them the other way, right? For example, 2 moles of water require 1 mole of oxygen, right? These are just relationships. It doesn't mean that I have 2 moles of hydrogen. It doesn't mean that I can make 1 mole of 2 moles of water, right? These are just relationships from the equations. Yes? Okay. Note that since these are mole relationships, right, remember that moles are really just tying back to Avogadro's number, right? A defined number of particles. If I wanted to, I could also say 2 molecules of hydrogen react with 1 molecule of oxygen. Or I could say 1 molecule of oxygen could produce 2 molecules of water, right? Because again, moles are just a scaled, defined number of particles. Okay. All right, let's do some practice together. All right, Skill Builder 8.1. Water forms when hydrogen gas reacts explosively with oxygen gas according to the equation. So how convenient, we've already got an equation that is defined. So how many moles of water, so here's our question or our goal. From the complete, how many moles of water result from the complete reaction of 24.6 moles of oxygen? Assume there is more than enough hydrogen, right? So what that's saying is, just like a recipe, if I'm going to start with just oxygen, there must be ample hydrogen, right? And so if I only have one piece of information, then I'm going to have to assume that there's ample of the other. Yes, does that make sense? Okay, So let's first come up with a relationship between oxygen and water, right? So oxygen, water. What that says is that for every 1 mole of oxygen, I can produce 2 moles of water. That is a relationship defined by that equation. And that's my conversion factor that I'm going to use. So I'm going to start with my 24.6 moles of oxygen. And then just like every other conversion factor to date, I'm just going to line things up so they cancel, right? I need moles of oxygen to cancel, and I convert to my 2 moles of water up top. Moles of oxygen cancel. I've converted to moles of water. 24.6 times 2 gives me 49.2 moles of water. And what this says with words is that I could produce 49.2 moles of water from 24.6 moles of oxygen. Concept check 8.1. Okay, so first let's dissect the problem. So methane undergoes combustion. We've got a balanced equation. If the figure on the left represents the amount of oxygen available to react, meaning that this is our given, the thing from which we'll start, which of the following figures best represents the amount of CH4 required to completely react with all the oxygen? So this is my given, and this is our goal, right? We would like to know how much CH4 is going to react with that much O2. So this is just a ratio, right? Just like we talked about before. Like, so we talked about here, right? We can write this relationship and use it, right? We talked about how we can write all of these relationships. This is the same thing. So what we'll do is we will take our 2, and what can we call these, right? We could say molecules of O2. And if we look at our balanced equation, for every 2 molecules of O2, that requires 1 molecule of, correct, 1 molecule of CH4. So then we'll just fill that in, right? So for every 2 molecules of O2, and for every 1 molecule of CH4, right? Which means that those cancel, that cancels, which means that we would require, oh, not 2, sorry. This is 4, which means this would be 2 molecules of CH4, right? Which then gives us this. Yes, does that make sense? And again, this goes back to what I said previously, where moles, right, is just a scaled up, defined number of particles, right? And which is why we can use this as a molecule or mole ratio, depending on what we're trying to do. All right, Skill Builder 8.2, magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to the reaction. So here's our balanced equation for us. How much HCl in grams, right? So this is our goal, can be neutralized by 5.5 grams of magnesium hydroxide, and this is our given. What makes this one different or slightly more thoughtful than the previous one? Right, we've just added one more step really on both ends, right? In that instead of starting from moles, now we are starting from a mass, right? And in order to use a mole ratio, right, because this is magnesium hydroxide, which is like substance A, HCl is our substance B, and in order to get from A to B, we have to use a mole ratio, right? So if we go back up to our equation, we know that 2 moles of HCl are equivalent to 1 mole of magnesium hydroxide, which means that we know that we have to get to moles. And how do I get from grams to moles? That's right, we would use the molar mass. So let's go ahead and start with our given, right? So 5.5 grams of magnesium hydroxide. All right, so we've got our given, and then in order to go from grams to moles, we will use the molar mass of magnesium hydroxide. And once we've got that filled out, because again, step 1 is grams to moles, then we know that we've got to get from moles of magnesium hydroxide to moles of HCl, and we will use our mole ratio to do that, which we've conveniently written down. So we'll just go ahead and take that and fill that in. And now we've converted to moles of HCl. So next we need to get to mass of HCl. In order to do that, we're going to use the molar mass of HCl. So all we're doing is layering things we know on top of our new thing, which is mole ratio. And once we've got the molar mass of HCl, then we can just do the math and hopefully do it correctly so that we get to the right answer. Which once we figure it out, we will round to the right number of significant figures. Which should be 6.88 grams of HCl. Note that we also want to go back and do things like double check that everything cancels out, right? Same skills we've been talking about all year. And then so in words, what that says is I would need 6.88 grams of hydrochloric acid to react with 5.50 grams of magnesium hydroxide. All right, skill builder 8.3. Another component of acid rain is balanced equation already provided. And it says, assuming there is more than enough O2, because again, that's how all of these problems work right now, right? If we only have one component, the assumption has to be there's enough of the other, right? How much H2SO4 in kilograms, here's our goal, kilograms, forms from 2.6 times 10 to the third kilograms of SO2, which makes this our given. Now, if I want to talk about H2SO4 versus SO2, right, the only way to talk about substance A versus substance B is by using a mole ratio, which means I've got to go back to my balanced chemical equation and find my pieces, which says that 2 moles of SO2 are equivalent to 2 moles of H2SO4. Now, if I want to use a mole ratio, that means I've got to get my SO2 into, that's right, moles, right? Starting with our given, which is our 2.6 times 10 to the third kilograms of SO2. We're going to take that kilograms and turn it into grams using the conversion factor we learned way back in chapter 2 from kilograms to grams of SO2. Then we've got to get it into moles, which means, right, molar mass, figuring out the molar mass of SO2. And then once we've got the molar mass, we've converted our kilograms into moles. Now we can employ the mole ratio that gets us from moles of SO2 to moles of sulfuric acid. Now that we're in moles of sulfuric acid, we can use the molar mass of sulfuric acid to get to grams of sulfuric acid. And once we are at grams, we can use our SI conversion again to go from grams to kilograms, which is what the question's asking for in this case. Otherwise, it wouldn't matter and you wouldn't need to do that last step, right? Now we're going to make sure all of our units cancel, and we'll note that that 10 to the third also cancels, which makes our math a little bit easier. And if we check, indeed, all the units cancel, leaving us with kilograms of sulfuric acid. Then we just got to do the calculations correctly, round to the appropriate number of significant figures, and we should get the correct answer. So what that says with words is that 2.6 times 10 to the third kilograms of SO2 could produce 4.0 times 10 to the third kilograms of H2SO4. Yes, makes sense? So note that all of these relationships are based on moles, not mass, right? Which means that all we're doing is we're incorporating conversion factors from the previous unit, right? Which is how chemistry goes because it's cumulative. All right. Thank you for listening. Be good and stay tuned for the next one where we layer on some new concepts and vocabulary to this concept of mole ratio. All right. Thank you for listening. Be good, and I will see you soon. Bye.